Hello, this is Mrs. Salmingo. This lesson we're going to learn, again, we've been learning about series. So here's where we're still going to learn a lot of tests to prove if a series, diverges or converges. And this test is called the integral test. And the first part of these notes is the proof. Just to save time, we'll do the Salmingo way and you'll just trust me that it's true. The integral test, if you want to highlight this or circle this into your notes, integral test that says if you have a function that's positive, there has to be three parts: positive, continuous, decreasing. Okay, for all numbers greater than 1. Okay, then the infinite series, remember the sum notation, and the integral, they both converge or diverge. So it doesn't say where it converges to, it just says it has to be converging. So this particular test, basically what you're going to do is you find a function and you have to find if it hits the three categories: positive, continuous, decreasing. So step 1, does it hit all three? So these three: positive, continuous, that's the first thing you're going to do. If that's true, what you're doing is take the integral, and if the integral diverges, the series diverges. If the integral converges, then the series converges. So we're going to do an example here. Again, we're going to skip the first page. So here's a series. The series of 1 to infinity of n over n squared plus 1. So here's one that I have no idea if it's converging or diverging. And it's a series, so I can't really apply anything to it. So what I'm going to do is I'm going to do the integral test. So what I'm going to do first is see if it's positive. Well, here, I'll number it 1. Is this positive? Okay, is this positive? Well, I start with 1 and go up. If I plug in 1 and keep on going, you'll notice that I never get a negative number. It'll always be positive. So check. This is always positive. Okay, is it continuous? Or another way to think of this is there anything I could put in the denominator that would make it 0 in this particular case? And no, there's nothing that would make the denominator like an error. There's nothing that would do that. So this is positive and continuous. The third part is the one that's going to take you a little bit of time. The third part, they ask you, is this decreasing for all those from 1 over? So you're saying, like, how do I figure out if this is decreasing? I mean, 1, you can put into a calculator and see if it's decreasing, but we have to prove it's decreasing or not. So to see if it's decreasing, what I'm going to do is I'm going to take the derivative and see if after 1, if it's always negative. So this is, obviously I'm going to take a derivative. This is quotient rule. Okay, so by quotient rule, and let's just rewrite this into x's, so that's, this is something you're used to. Let me take the derivative and see if it's negative everywhere after 1. So if you remember to take the derivative of this one, what I'm going to do is I'll take the derivative of the first one, leave the second one alone, minus, leave the first one alone, derivative of the second one. And then that was all over the denominator squared. Okay. If I simplify this, again, I'm just going to simplify this for sake of time. You should get negative x squared plus 1 over that denominator. Okay, so I simplified it. You can do it on your own. That's what you're going to get. And you'll notice that for all numbers greater than 1, you can try putting in some numbers. If I do the test, okay, if I do a number line test, okay, if I did a number line test, and I tested numbers after 1, like plug in a number, plug in 2, plug in 3, plug in anything, you'll notice that you'll always get a negative number. So yes, this is also decreasing. So 1, 2, 3, it's positive, it's continuous, and it's decreasing. Okay. So now what I'm going to do is I'm going to apply the integral test. Okay. So if you don't have this, you could pause this, so you can rewrite this down. I'm going to erase all of this real quick. And let me apply my integral test. So again, the integral test, what I'm going to do is I'm going to take the integral and see if it's converging or if it's diverging. If it's converging, then the series is converging. If it's diverging, then the thing is diverging. So let's try this out. The antiderivative of 1 to infinity of the function, like so. You notice that this is an improper fraction. Also, you'll notice that I can't take the antiderivative as it is. I can't put this into partial fractions. This doesn't factor. So I'm going to do u substitution. So let's say u is x squared plus 1. Du is 2x. And half du is x dx, which makes this whole thing 1 to infinity of 1 over u half du. Okay, and then what I'm going to do is I'm going to take out that half, and you know the antiderivative of 1 over u is ln u. From 1 to infinity. And then what I'll do is I'll plug the x squared plus 1 back in. Half ln x squared plus 1. Oops. From 1 to infinity. Okay. So now, I got to figure out if this converges or diverges. So if you remember to tell if this converges or diverges, let's plug in the infinity, let's plug in the 1 and see where the limit goes to. You know that if I plug in infinity, this is going to be ln infinity squared plus 1. So this is ln infinity. And this will be ln minus ln 2. Right? And you know that ln infinity, or hopefully you know, is infinity. And infinity minus anything is still infinity. Half of infinity is still infinity. That means that this whole series, this integral diverges, and because the integral diverges, that means the series diverges, and that's how the integral test works. Okay, so let's just try one more example. I know there's 3 on your paper, but let's just do 2 to see if you get it. So all I did, just to review, I had erased it already. 3 tests: positive, decreasing, continuous, in that order. If those are true, I will take the antiderivative from 1 to infinity and see if it's converging or diverging. If it's true for the integral, it's true for this series. And that's all that you're doing in this step. So, again, let me erase this. And again, if you was going too fast, you could rewind it, you could stop it, you could slow me down, or you could take it a little time to write down the notes. Okay. So this one, same thing, I'll apply the integral test. Again, there's 2 things. Is this positive? Okay. So again, try plugging in some numbers, 1, 2, 3, 4. You'll notice that it never turns negative. This is positive. Step 2, is this continuous? Is there anything after 1 that would make this error? And again, no, there's nothing that would make this error on the denominator. And then the hard part, again, is this decreasing? You can put it into a calculator. Again, sometimes you don't have a calculator, so what I'm going to have to do is I'm going to take the derivative and see if it's negative everywhere. So again, I have a function that's a fraction, so I'm going to have to do quotient rule. So if I do quotient rule, derivative of the first one is 0. I'll leave the second one alone. Minus, leave the first one alone. Derivative of the second one. All over the denominator squared. Again, good review of the quotient rule. Okay, and then if I simplify this, again, you could just trust me, or you could simplify it out yourself. I get negative 2x on the top, and I still get that x squared plus 1 squared on the bottom. And again, think of this as an imaginary number line. I'll try plugging in numbers after 1 and see if it's always negative. Plug in 2, plug in 3, plug in 4. The bottom's always going to be positive, and the numerator is always going to be negative. So that's why, yes, this is decreasing. So all 3 are true, which means, yay, I could use the integral test. Again, if you didn't have time to take notes on this, you could pause this. I'm going to erase it. So now what I'm going to do is apply the integral test. The integral test says I'm going to take the antiderivative from 1 to infinity, and again, just for sake, I'm going to put x squared plus 1 dx. Now, this particular problem, I can't do u substitution. I can't do anything. I tried teaching this before, but you may have forgotten. But this is an example of a trig substitution where I have a 1 over x squared plus 1, which is the same thing as the derivative of arctan, or tangent inverse. So this is arctan of x from 1 to infinity. So if you remember your trig derivatives, the derivative of arctangent was 1 over x squared plus 1. Okay, so you may have forgotten. So now all I do is plug in infinity and plug in 1. So I get arctan infinity minus arctan 1. Okay. You might need a calculator for this. You may have forgotten. Arctangent infinity, it goes towards pi over 2. And arctan 1 goes towards pi over 4. So doing some basic math, some basic fractions, some algebra 1, you're going to get pi over 2, because this left one is 2 pi over 4. So 2 pi over 4 minus a pi over 4 gives you just 1 pi over 4. So here's where I want you to be very clear. This converges to pi over 4. This integral converges to pi over 4. The integral test does not tell you where the series converges to. It just says it converges. So in this particular case, okay, so if there's anything I want you to pay attention to, well, everything, but in this particular case, make sure that you know that this integral converged. So that proves that the series converges, but it does not prove that it converges to pi over 4. The integral converges to pi over 4, but the series, we don't know where it converges to. All you need to know is that it converges, but we don't know where it converges to. So hopefully that's clear. We'll do some practice in class. If you have any questions, you could ask me in class. But other than that, thanks for watching, and I'll see y'all later.